nuts, right? And that's true in game theory as well. Often in game theory, you can get these weird things with multiple equilibria. But if you have more smoothness, so for example, if people are heterogeneous or you have incomplete information, that often creates an equilibrium where one didn't exist. Often you were looking at a simpler game to make things simple, but then that made you have all these problems that made everything complicated. If you actually add more heterogeneity, add more imperfect information, that can often smooth things out. In general equilibrium theory, this is particularly true because the whole idea of general equilibrium theory is that there's a large number of people. And even more broadly, to a large extent, when you find that equilibrium doesn't exist, a lot of people interpret that as, oh, this market's going to be crazy, it's not going to work at all. That's a silly conclusion to come to. The right conclusion to come to is that you have the wrong model if the equilibrium is not existing. OK. So the main point of all this is don't be a slave to definitions and formalism and just solve something out, come to a problematic conclusion, and just stop there and say, oh, that must mean that the world is messed up. Reflect on what led you there and try to figure out where you went wrong in making your assumptions. OK. Now let's talk about comparative statics. So what should we expect to happen in a model, in a market, when the supply rises? Jim, this is Econ 101.
You'd expect the price to fall.
Exactly, right? So you'd expect the quantity to rise and the consumer price to fall, right? And this is just classic supply and demand, right? Now, this is still going to be true when we think about things very generally, but it's a little bit more subtle. So let's look at this mathematically. So imagine that there's just a single market equilibrium, and we have supply equals demand. And there's some supply shifter, S, right? So how much does the price change when the supply shifter changes? Is Luca here? Yeah. Does anyone else want to derive that from the above equation? This is Econ 101. Come on. How much does the price change when supply changes? What's dPdS? Anybody? Jim.
1 over T prime minus S prime.
Exactly. Right? So we take the implicit function theorem. We do, d prime times dPdS equals s prime times dPdS plus 1. Divide through and you get 1 over d prime minus s prime. So this is actually the classic elasticity formula, right? You can just turn these into elasticities by normalizing them the right way, right? And as Jim was saying, this should be negative if there's any justice in the world, right? The price should fall when supply increases, right? And of course, that's going to be true if demand slopes downward. This is negative, and this one's positive, right? But that's not necessary for this to be true. In particular, the key thing is that demand has to cut the supply curve from above to below, right? And the reason why that just has to be the case is that otherwise, if the price were to rise a little bit, then we would get a situation when, rather than supply being greater than demand, demand was greater than supply. And when there's excess demand, you should think, well, the price should rise more. But then it would get even more out of whack, and things would go crazy. In other words, that equilibrium point wouldn't actually be an equilibrium. It would be a sort of like the least likely point for the market to settle on, rather than the most likely point, right? So in particular, let's call the difference between demand and supply the excess demand, E of P. For the market to be stable, E of P has to be decreasing. So let me just show you a picture of that. Suppose that I've reversed the standard axes so you can see it more clearly. Demand cuts supply from above to below, which is what we said things have to be, right? Then if I raise the price, then the supply gets greater than the demand, and we're pushed back towards the equilibrium. If the price gets below, the demand gets greater than the supply, and we get pushed back up towards the equilibrium. And under that case, even if both demand and supply are decreasing, which we shouldn't usually think, right? We usually say the supply curve always increases. But even if demand and supply are both decreasing, we still get the right comparative static that if supply increases, the price is going to fall. On the other hand, if we're in this crazy situation when supply cuts demand from above to below, rather than demand cutting supply from above to below, and things were unstable, so if we went to a higher price, then actually demand would be greater than supply, and we would go to an even higher price, and things would go away from that, then we get the opposite. And actually, when supply increases, price increases. But the only reason that that happens is that this is an equilibrium that doesn't make any goddamn sense to think about. It's not even an equilibrium, right? And that's exactly what we should expect to happen. So let's think about what would occur in an individual maximization problem. So suppose an individual maximized f of x minus t of x, where t of x is some shifter that makes him less inclined, like an increase in a price, right? We know that x star has to fall when t increases by revealed preference, right? Because the person could always have chosen the larger value of t before, and now he's strictly more penalized for doing that, right? So he's always going to decrease x when t increases. Now, the optimal choice of f, if this is differentiable, gives us f prime of x is equal to t. And so what is dx star dt? Raluca is not in the class, is it? Is she? Anyone else want to do that? This is even easier than what I asked Jim to do. Come on. What's dx star dt? Somebody. What's your name again? Carl. Yeah, Carl. Yeah. It's the second derivative of f, right? Good. It's 1 over f double prime of x, right? So this, again, is going to give you the right sign if and only if f prime is less than 0. And why is that? Well, the thing's only a maximum if f double prime is less than 0. Otherwise, you're looking at a minimum. And of course, if you're looking at a minimum, everything's going to go in exactly the opposite direction, right? Because if you make something less pleasant, people are going to do more of it if they're trying to minimize their utility, right? So what that says is that stability in an equilibrium is really just the same thing as the second order conditions of an individual maximization problem, right? And it's locally equivalent to comparative statics. That is, we get comparative statics that make sense if and only if we're looking at a stable equilibrium. And what is the relationship like this for second order conditions? Is Anushri here? No. Anyone else want to talk about what happens with global second order conditions? Well, if we have this second order condition, f double prime is negative everywhere, then we know that any solution to this first order condition is the global maximum, right? Because the function's concave. And so whatever point is its critical point is the maximum, right? And in fact, we know that for any value of the tax, that will be the case. Similarly, in fact, if we know that this is, that any solution to this is the global maximum for every value of the tax or price, then we also know that this function has to be concave. Why? Otherwise, we could adjust the tax so as to satisfy the first order condition at the point where it wasn't concave, and that would clearly not be a global maximum. It would be a local minimum, right? So there's an equivalence between comparative statics and the local second order condition, and between the global second order condition and this sense of like any solution to the equation is the global maximum, right? Okay. Both of these ideas extend to stability in equilibrium. So when it's not an individual maximization problem, when it's an equilibrium, both of these things are true. There's an equivalence between local stability and comparative statics, and there's equivalence between global stability and any solution being the unique equilibrium. Unique stable equilibrium. Okay. However, there's two key things that change when we talk about stuff that we usually call general equilibrium. And in my view, these two things are the only difference between general equilibrium and partial equilibrium. The first difference is that there are many markets rather than just one market, right? And is Zianis here? No. Does anyone else want to talk about how the things that I was just discussing might get a little bit more complicated if there are many markets? Think about what happens when there's many goods that an individual is choosing in an individual yeah, go ahead, James.
So our supply, the gap between our supply and demand function, the first derivative of those, we might no longer expect that to be greater than 0, because when the price of this good changes and the demand for that changes, then it can affect demand in other parts of the system, which can have sort of knock-on effect throughout the system, and we're not sure what the general equilibrium outcomes.
Yeah, so there's all sorts of stuff going on, but luckily linear algebra lets us simplify that down. And the key thing is that we just need to use negative definiteness rather than just negativity as the equivalent here. So if we had a multidimensional system, then the equivalent is now not that the excess demand, the derivative of the excess demand is negative, but rather that the gradient of the excess demand is negative definite. The same way that we would say that the Hessian has to be negative definite rather than just f double prime being negative, right? So that's actually not such a bad complication. So we know sort of how to deal with multidimensionality in an individual maximization problem. We just move from negativity to negative definite. On the other hand, there's another problem which comes from the existence of income effects. And Eric, do you know what that problem is? So what is required for something to be negative definite? Exactly. And why can we just look at the leading principal minors? Why don't we need to look at all of them? Because the matrix is symmetric. And what is not true when there are income effects? Yeah, you don't get a symmetric matrix, right? So that is a key difference between equilibrium and an individual maximization problem when there are income effects, right? When you have one of these market equilibria and there are income effects, the gradient of the excess demand function is not going to be a symmetric matrix. And so there is no natural notion of some negative definiteness, right? Now, in one dimension, that doesn't matter, because there's no such thing as symmetry versus asymmetry in one dimension, right? In many dimensions, the gradient of the excess demands doesn't need to be symmetric. And so there's a whole art associated with finding what is the right extension of the notion of negative definiteness to this case when the matrix is not symmetric. And that is what the note that you were assigned, but probably nobody read, talks about. In particular, there's this notion called d-stability that shows up in this more general context. And everything that I just told you, all those simple things about the relationship between comparative statics and uniqueness, extend to this context, but you just have to use the right notion of negative definiteness.